last lesson of the day. Limits at infinity. So this is a bit of semantics. Limits at infinity, this means your x goes to some kind of infinity, okay, versus an infinite limit, and this means the limit equals some kind of plus or minus infinity. Does that difference make sense, what I mean? So we've seen examples of this. So for example, the limit as x goes to 3 plus x over x minus 3. That limit would be positive infinity. That's an example of an infinite limit. Versus the limit as x goes to infinity of a function is equal to something like 3. So in this one, you're plugging in numbers that are closer and closer to 3, right? If your limit's going to infinity, you're plugging in numbers that keep getting bigger and bigger and bigger and bigger. Does that make sense? You've got a limit of x going to a number. It's like what happens as you get close to that number. This is what happens as x gets close to infinity, which means x gets huge, okay? If you had a limit as x went to minus infinity, that means x gets huge and gets negative. Does that make sense? Okay. So dealing with these will have its own kind of special set of like techniques that work well. So it's the intuitive definition of a limit at infinity. So you've got a function defined on some interval, and the limit is equal to L, which means that the values of your function f of x, or the y's, can be made close to that L value by requiring x to be sufficiently large. So here's a picture. There's your y equals L line, and your function gets close to it from the top. Your function could also get close to L from the bottom. You probably haven't ever seen examples of functions that cross their horizontal asymptotes yet, right? And the reason is because most of the functions that you've seen that have horizontal asymptotes are rational functions and they don't cross their horizontal asymptotes. But a function could do something like this. It could oscillate, but the oscillations could dampen. Do you see what I mean by that? And they kind of keep shrinking. And in all those cases, as the x's get large, the y's get close to L. So close to doesn't specifically mean that your L has to be only above or only below that L. You can cross your horizontal asymptotes. It's totally possible. You just haven't seen examples of it. Okay. And that line, y equals L, is called a horizontal asymptote, right? So the definition of the horizontal asymptote is if the limit as x goes to positive infinity is that number, or x goes to negative infinity is some other number. So to check for horizontal asymptotes, you've got to actually check positive and negative infinity. And in the case of rational functions, they end up being the same thing, but they're not always the same thing. So there are functions like that could do something like this. So say here's the line y equals -2. Here's the line y equals +2. And that function has two horizontal asymptotes. It approaches one as you go to positive infinity and one as you go to negative infinity. Okay? So when asked to check horizontal asymptotes, you do have to check both unless you've got good reason to believe they're the same thing, and then you must explain that. The next example is your favorite function, your favorite inverse trig function. The only inverse trig function you know what the graph looks like. So what does y equals tan inverse look like? It goes through the origin.
X approaches negative infinity is equal to negative pi/2.
Yeah.
And the limit of x is x approaches infinity equals pi/2.
Yep. what we're saying here is that there are horizontal asymptotes at positive pi halves and negative pi halves, right? And it does the snaky thing that I just drew a picture of on the last slide. Okay. So what is the limit as x goes to infinity of tan inverse of x? As x's get really, really big, tan inverse gets closer and closer and closer to pi over 2. And as x goes to negative infinity, inverse tangent gets closer and closer to negative pi over 2. So for that, it's a great way I could like ask that question at test and say, okay, sketch tan inverse and then blah, find these, right? I mean, like if you can't sketch tan inverse, you can't do the limit thing. Oh man, okay. Okay, find the infinite limits, the limits at infinity, and the asymptotes for the function f whose graph is shown below. So here are the infinite limits. These are the limits which equal plus or minus infinity. And there are going to be, how many places is the limit plus or minus infinity? 2. Okay, the first place is at x equals 1, right? Or no, sorry, x equals negative 1. Does the limit approach the same kind of infinity from both sides? I think it does. Not at the next one, but at x equals negative 1 it does. So the limit as x goes to negative 1 of f of x is infinity. And there's no need to state that two-sided because the two sides go to the same place. Is that okay? There's no need to state this in two cases. So no need to specify that, okay, negative 1 from the left, negative 1 from the right, because from the left and right they both go to infinity. But with this one, to explain what the graph is doing, you have to say, okay, as I go at 2 from the left, the limit is... So limit x goes to 2 from the left of function equals negative infinity. And limit x goes to 2 from the right is positive infinity. And those you must state separately because the behavior is different on different sides of 2. Okay? So those are the infinite limits. And the semantics of the wording, I do agree, is like quite tricky. You've got to be really careful what you mean. How about the limits at infinity? So that's what happens as x goes to infinity or negative infinity. So what's the limit as x goes to infinity of this function? 4. You can tell that because as you approach this way, you're approaching the line y equals 4. We're assuming the function does no funky stuff outside of the screen that you've seen, which is a big assumption, but we'll just pretend. Okay, how about the limit as x goes to negative infinity? 2. Because over here, your function appears to go down and approach y equals 2. Asymptotes, okay. Okay, so what are the asymptotes of this function? Be a little bit specific, okay? Is it great? X equals negative 1.
And x equals 2.
Good. Okay, those are the vertical asymptotes, right? What are the horizontal asymptotes?
Y equals 4 and y equals 2.
Good. No need to specify, like, you don't have to say VA or HA. If you say x equals and y equals, the fact that x equals is a vertical line means it's a vertical asymptote, right? That's why I was a bit picky about you saying x equals when I asked for vertical asymptotes, because you shouldn't just say, okay, it's 1, you should say, okay, x equals -1. Oh, it's not clear if you mean a vertical or horizontal line. Okay. Now, some of these things should be somewhat intuitive. If you take a constant divided by a big number, what does that do? Makes constant divided by big number makes small number, right?
Yes.
Which means small number meaning 0, right? So something like this, I have 1 divided by 7x plus 1. Think about it. You could plug in numbers that kept getting bigger and bigger and bigger and bigger for x, right? You're going to get 1 divided by a larger and larger and larger number, right? So that limit is going to be 0. Does that make sense? 1 divided by 1 over big number makes 0. Doesn't even matter if big number is negative, right? If you do 1 divided by -1,000,000, you get -1,000,000th, which is still going to 0 eventually, just from below as opposed to from above. Okay? How about sine? As x goes to infinity, does sine make up its mind and go one place?
No.
No. This limit does not exist. That function is bounded, like it doesn't blow up in a different way, but it doesn't go one specific spot. Okay. Part C is kind of like part A in disguise. What I mean by that, this is the same thing as limit x goes to infinity 3 over e to the x, because that's what negative exponents are like, right? And what happens when you plug big numbers into e to the x? It goes huge, right? E to the 1,000 is like ginormous, your calculator can't do it, right? 3 divided by big numbers makes 0.
Usually gets to 0 a lot faster.
It gets to 0 a lot faster than, say, part A does. Another way to think about part C is if you were asked to graph 3e to the negative x, isn't it the e to the x function but just decaying instead of increasing? It's a reflection over the y-axis. And from the picture you can say, okay, well, as my x's get huge, that goes to 0. What happens as the x's get hugely negative? It goes to positive infinity. Okay, so it's possible that from one direction you go to 0, the other direction you go to infinity or a different number. Okay. So I'm going to skip that and just explain by examples. So have you seen stuff like this and found out a way to find the horizontal asymptotes? I took away the limit sign, pretend that it's not there for a second, and said, okay, find the horizontal asymptote of y equals 2x plus 5 over x minus 4. Were you taught that this has an HA at y equals 2? Yeah, okay. Here is the reason why. So technically, when you plug in infinity, you get infinity divided by infinity. Does that make sense? You get big number divided by big number. Now, much like 0 divided by 0 isn't always 1, infinity over infinity isn't always 1 either. Okay? So how you can prove that this limit is 2 is you can multiply the top and bottom by 1 over x. So just do that for now and tell me what you get. What's 2x times 1 over x? 2 plus 1 over x times 5 will give you
5 over x.
1 minus 4 over x. Is everyone okay with the fact that that's a legit operation? That seems like an okay thing to do? All right. Well, you don't get, actually not quite. So now as x goes to infinity, what happens to, that's 5 over x, not 5 times x. So that's now 5 over big number.
That was like a 0.
So that goes to 0, right? What happens to 4 over x? Goes to 0. So this is going to equal 2 plus 0 over 1 minus 0, which is 2. And that's because 5 over x goes to 0, 4 over x goes to 0. And you know that, okay, 5 divided by a big number, definitely going to be 0. 4 divided by a big number, going to be 0, right? And that's how you sort of, that's like the long way to prove, or really the reason that you can use those asymptote rules you may have learned in Algebra 2. On WebAssign, I don't care if you can do these quickly and can do them in your head, okay? That's fine, because the check is like, do you understand? On your written homework, you must, for now, show me that little step. Does that make sense? So show me that you multiplied by 1 over x, what you divided by x. Do you get that? That's how you kind of prove this is true. If you see the patterns on a WebAssign, you can use them, go ahead and apply them to save yourself some time. I'm not trying to make you like suffer so much. A little bit, not a lot. Okay, let's try another. Okay, well before I start this one, I'm gonna multiply together that denominator. Does that make sense? If you could cancel some stuff, that would be great, but there's no canceling that can happen here, is there? Okay, so limit x goes to infinity, x squared plus 4 over, I think that's x squared plus x minus 12. Do you agree with that multiplication? Okay. Now, in the previous example, we multiplied by 1 over x, because I took our highest power down to being a constant. What do you think you're going to multiply by here? 1 over x squared. Okay, so that's the limit x goes to infinity, 1 plus 4 over x squared over 1 plus 1 over x minus 12 over x squared. Does that make sense?
If that was just x to the third, you'd do 1 over x to the third.
Exactly. Yep. That was kind of trying to explain the pattern, is like multiply by the reciprocal of the highest power. And if they're not the same power, we have to do a little bit more trickery, okay? But for now, when they're the same, is the highest power. So what's going to happen to the 4 over x squared? Where's that going to go? 0. How about the 1 over x? How about the 12 over x squared? 0. So this limit will be 1. Does that jive with the rules you learned in like, say, pre-calculus or algebra 2 and finding horizontal asymptotes? It does, right? But now that you know limits, you're expected to sort of know where those rules come from, not just memorize them blankly because your teacher said so. Which is kind of what pre-calc was like. I was like, just learn these rules. There's these patterns. Awesome, guys. Isn't this cool?
Hey, I could go on to rate my professor and give you a 1.
Go for it. I don't care. Okay. I care a little bit, but this is a non-representative sample, so it's all full of biases. So, how about this one? What would you multiply by? One over x squared, okay. Becomes 2 plus 5 over x squared over 3 plus 1 over x squared. So where's that going to go? 2/3. Okay.
The second part always goes away, right?
Say that again?
The second part always goes away.
As long as you have a constant over an x in the denominator, those will always go to 0.
As long as they're constant.
As long as they're constants. And in this case, they're almost always going to be a constant over x. Yeah, this section really, there's not very much. It's not really that bad. It's not that hard. There's no trickery. If it's a 5 over x or 5 over x squared, it just one goes to 0 faster than the other, but they do still go to 0. Does that make sense? Kind of like you said, how e to the negative x will go to 0 faster than 1 over 7x plus 1. Same kind of idea. This one is the first one we've seen where the powers don't match, right? They're not the exact same. So you can do this one of two ways. I think it's easier to look at the 2 and take the lowest power and multiply by 1 over that. So what's the lowest power comparing the numerator and denominator? X. So multiply by 1 over x and 1 over x. 2 plus 5 over x over 3x plus 1 over x. Is everyone okay with at least the simplification of that stuff? Okay, so as x goes to infinity, what happens to the numerator? What does it go to? Goes to 0 or 2? 2. So the numerator goes to 2. What happens to the denominator? It goes to infinity. 2 divided by a big number makes 0. So that limit is 0. Just in case you do it the other way, let's just see what would happen if you multiplied by 1 over x squared, okay? Because it will look a little bit different, but you're going to have the same conclusion. Okay, so if I do 1 over x squared, 1 over x squared, what does that make the numerator? What's 2x times 1 over x squared? 2 over x plus 5 over x squared, right? What's the denominator going to be? And in that case, where's your numerator going? Denominator goes to 3. 0 over 3 is also 0. So it doesn't matter which one you choose. Does that make sense? I just tend to prefer the lowest of the two. It's just me. I mean, it doesn't matter. They both work.
Make less mistakes.
Yeah, I mean, I think it's completely up to. I think it's completely up to the individual. They both. I just want to show you both in case you do the other way, just so you know how to deal with it. Okay. And in algebra 2 or pre-calculus, didn't you learn that the denominator's power was larger, the limit was always 0? And that's going to be true for everything. So if you can spot that pattern on your homework or WebAssign, go ahead and just say, okay, yeah, this is 0, I know it. On written homework, show me one of those two ways. Okay? Okay, so this one, so I think picking the lowest of the two and going with it is really the best method. So in this case, what we multiply by? Top and bottom. 1 over x squared. And it really is this case that the other way ends up being a bit confusing. So this will be 2x plus 5 over x squared over 3 plus 1 over x squared. And what happens to the numerator? Where does that go as x goes to infinity? Infinity over 3, right? Which still makes infinity. Here's the reason the other way is confusing. Okay, so multiplying by 1 over x cubed, it'll work, it's just you have to be a bit clever about the interpretation. It becomes 2 plus 5 over x cubed over 3 over x plus 1 over x cubed. Do you agree with that math? And then you're going to 2 over 0. Does that make sense? And it's also technically it's 0 plus because these are both positive zeros. Does that make sense? So this is also infinity, but I think it's harder to interpret that way than the way I did it first. You see that that's a little bit more confusing? So I think picking the lowest of the two powers is the best way to go. That's my personal preference. That'd be what I recommend. But if you do it the other way because you forget, just be aware that that's how you would interpret it. Okay. So in these, I multiplied by 1 over x squared. And the thing to notice is that infinity divided by infinity is just not always a consistent number. So in the previous example, the numerator goes to infinity so much more quickly than the denominator that it dominates and makes it so the limit is still infinite. Okay, so this one, how could you kind of make it like the previous one? What could you multiply by to make it so you could figure out that you don't have infinity over infinity? 1 over e to the x, yep. limit x goes to infinity, 1 over e to the x plus 5 over 7 minus, 7 over e to the x minus 1. Okay. So where do the 1 over e to the x and the 7 over e to the x go as x gets large? 0. So this goes to 0 plus 5 over 0 minus 1, or negative 5. Okay.
I have a question.
Yes.
I know you said that you can't do infinity over infinity, but if you were to plug in infinity for the x, when you get infinity over negative infinity, wouldn't that just be negative?
No, that's the answer is no, it's not. It just does not work that way. You just can't divide infinity by infinity the same way you can't divide 0 by 0. So limits are how you deal with that. And it really has to do with the fact that infinities have different sizes. Some of them are bigger than others. And that the reason how that works is quite technical. Okay, so in this one, the picture of ln looks like this, right? And as x's gets large, ln goes to infinity. Does that make sense? If you shift those functions over, they're still going to go to infinity, right? The y's keep getting bigger and bigger. They get bigger slowly. So as x goes to infinity, this is kind of like infinity minus infinity. Is that going to always be 0? Probably not. So this is not equal to 0. Occasionally it equals a number. Occasionally it is 0, but just not always. Not 0 always. So you've got to figure out how to deal with that. And, well, we've been doing a lot with fractions, and I put this on there because I want to make sure you review your rules for logs. What happens when you have 2 logs that are subtracted? How can you make them into 1 log? 1 log, and then the numerator is 2 plus x. The denominator is 1 plus x. Okay, does that make sense? Okay. Now this is kind of like the thing we had in the previous section where limits can go inside of continuous functions. Natural log, as long as it's defined as a continuous function, right? So this can become ln of the limit as x goes to infinity of 2 plus x over 1 plus x. What you can do is find the limit of this stuff and then take the natural log of whatever it is. Kind of like how we, took the limit of the stuff inside that sine function by plugging the number in and then did whatever we had to on that number. So technically inside of that ln sign, you would multiply by 1 over x, and you'd get 2 over x plus 1, 1 over x plus 1. So what's the stuff inside that limit going to? 1. So this is ln of 1, which in this case does actually equal 0. Okay. Is everyone all right with that? All right. Okay.
I think I want to just jump early and put infinity in there.
And just, yeah,
And
so.
end up with 2, all of 2.
Yeah, but the thing is like if you have 2 plus a big number, 1 plus a big number, it's almost the same number divided by itself, right? If you want plugging in like a million and 2 divided by a million and 1 is awfully close to 1. So it isn't the thing, it's the things that affect what this number will be are the highest powers, not the lowest powers. So some people in some books will just say ignore all the lowest powers, look at the highest powers only, and see what happens to those. I think that's how I taught my pre-calc kids to deal with those horizontal. I think I said take just the biggest powers, ignore everything else, reduce that, and see what happens. Okay. This one's weird because of the square root sign, right? Do you agree? Okay, and so when you look for the highest power of numerator and denominator, you gotta kind of factor the root in. So if I ignored the 9 and the plus 1, the denominator's power is like root of x squared, which actually is x, okay? So we're going to multiply by 1 over x and 1 over x. Okay, so the question is, what happens when 1 over x goes in the square root sign? And if you know, don't answer yet. So, and that's related to what happens if you say, take root 8, okay? Simplify that. You say 8 is 4 times 2, right? Which reduces to 2 root 2, okay. So, it's not a great example, but what happened to the 4 when it came out of the root? It was rooted. So if you wanted to put it back in, you'd have to square it. So it gets squared. Does that make sense? Something comes out, it gets rooted. To go back in, it gets squared. To the opposite, it gets squared. Okay? Okay, so that becomes the limit as x goes to infinity. What's the numerator? Great. And the denominator, when that 1 over x goes in, it becomes 1 over x squared. You don't have to state that step. What I'll really be checking is your next step correct? Like, do you have 1 plus 2 over x over root 9 plus 1 over x squared? Do you see what I mean by that? Like, I'm going to be checking, do you have 1 over x squared there? Because if you had 1 over x, you're going to get the same conclusion, but you got the same conclusion because you're lucky, not because you're 100% correct. Okay, so now what happens to the numerator as x goes to infinity? Where does this go? 1. The denominator goes to square root of, root 9, but, which then roots to 3. You were just a step ahead. So it's not super hard, but the point is when stuff goes back into roots, it gets squared. And to just remember, like what is x cubed squared? What happens when you x to the 6th, right? Remember, exponents multiply, so when you square an exponent, it doubles, right? Okay. Okay. So multiply by what in the denominator? And also same thing in the numerator. Okay. So the denominator is the easy part. That's going to be 1 plus 1 over x cubed. What does that power become when it goes inside of the root? X to the 6th. Okay, so that's going to be root 3 minus 1 over x to the 5th over 1 plus 1 over x cubed. So what's that going to equal? Root 3, yep.
I don't want root 3 equals.
It is root 3. We will want root 3. Root 3 is good enough. If you web sign asks for a decimal, give it one, but I probably won't, so just give it root 3. Okay, great. So far we've only done positive infinity, right? I haven't dealt with, other than pictures, we haven't dealt with negative infinity at all, yes? So this is my method, and I think it's a good one. Your book doesn't do it this way. Maybe they do. I don't know. I didn't really look all that carefully. So if x gets huge and negative, does it make sense that it's the same thing as first make x negative, then make x big? Like break it down that way? If x is going to big negative numbers, you can first account for the negativity by making x is negative, and then you can go to a big number. And that's what I mean. So replace your x by negative x. That takes care of the negativing. And then you can take the limit as x goes to positive infinity. So you reduce it to something that you can actually understand.
So basically times it by
not quite times it by a -1, but input -1. Because sometimes plugging in x and negative x will be the same thing, like when you have a squared number. Does that make sense? So this means really, it's kind of like the even oddness. So input negative x, and then as x go to infinity. Okay, so this one. So the limit as x goes to minus infinity is the same thing as the limit as x goes to positive infinity, but we're going to input negative x's everywhere. And then I think you can convince yourself that plugging in really, really big negative numbers here is the same as plugging in really big positive numbers over there. Does that make sense? Because the negativity is taken care of by the negative x's. And then can you simplify those things a little bit? You can make it into negative 2x over root positive x squared plus 2, because a negative squared makes positive, right? And that's pretty similar to the previous ones that we did, right? So multiply by what? 1 over x, great. And that's the limit. X goes to infinity, negative 2 over, okay, x squared plus 2, 1 over x squared. Negative 2 over root 1 plus 2 over x squared. So I think this limit is negative 2. Okay. So the best way I think to deal with negative infinity is to manipulate the limit so you can make it positive infinity instead. And that's sort of separate out the negative bit and the getting big bit.
How'd you get rid of that negative in the root?
Oh, because negative x times negative x makes positive x squared. Right? Negative x, the quantity squared, is the same thing as minus x times minus x, and a negative times a negative makes a positive. Right? No matter what x is. Whereas the numerator, 2 times negative x is negative 2x.
So it's actually,
If it was a third power, it would have remained negative.
so you'd leave it in there?
If it was negative x to the third, you'd say, okay, that's negative x cubed. Yep. So the negative stays, but you don't need to keep in parentheses anymore. You can think about that as being negative 1 times negative 1 times negative 1, which makes negative 1, and then x times x times x cubed. Okay. Same idea here. So limit x goes to infinity. What does the stuff become when you input negative x? Don't do any fractions yet. 5 minus. Okay. When you make this into a fraction, it's 5 minus 3 over e to the x. I'm not sure if that's what you were saying, Natalie, but it just makes the 3 and the e to the negative x into its own fraction. The e to the x doesn't go underneath the 5. Okay, so where's this part going to go as x gets huge? Just the second part. Limit x goes to infinity of 5 minus limit x goes to infinity 3 over e to the x. This goes to, in bottom gets big, 3 over big number makes really small, so 0, crazy small. 5 minus 0 will make 5. Is it clear why the first limit is 5? So think about just that. It's a y equals 5 is a horizontal line, right? As x goes to infinity, the y is always going to be 5, right? Okay. Yeah. And this next one, just for time, I'm just going to do the first one of these. So this is kind of a combination of the whole, when stuff goes into roots, it gets squared. And it's a tricky conjugate thing. Now, is it first of all clear that when you go to infinity, what you're kind of getting here is infinity minus infinity? Like this thing's getting big, this thing's getting big, right? Okay. So the way to deal with that is actually to use a conjugate. It's pretty clever. Multiply by root x to the fourth plus 6x squared plus x squared over same thing. And you have to multiply by the conjugate over itself because you're multiplying by 1. That doesn't change anything. And what this will also accomplish, it will take something that was not a ratio for you originally, and it's going to make it into a ratio, which means we can deal with it like we did with the previous stuff. Okay. So what do you get when those numerators multiply together? X to the fourth plus 6x squared, and then minus x to the fourth. And those x to the fourths cancel, right? So you'll just have limit x goes to infinity 6x squared over root x to the fourth plus 6x squared plus x squared. And you've made it into something that you can deal with. Okay, so what do we multiply by now to deal with the whole infinity over infinity business? Mm-hmm. Okay. And I'm going to be slightly lazy and skip a little bit of steps here, so if you get confused, please just let me know. The numerator becomes 6, right? And obviously you got this, we got a plus 1 hanging out at the end. Do you buy that? Okay. When that 1 over x squared goes into the root, what does it become? X to the fourth. So x to the fourth over x to the fourth is going to make 1. And this is going to be 6 over x squared, right? Do you buy that? Okay. So now can you, without any like qualms, say what that limit's going to be? 6 over 2, which is equal to 3. Is that all right? Okay, this is a tricky trick, okay? Yes?
Does it always have to be a ratio?
To use this trick, it does have to be a ratio. So I don't know of any other way to do this particular problem. Does that make sense? Like I am not withholding some information from you. I have never seen a student make up a different way that actually works. Okay, so this is the trick that I know works. I don't know if there's another one. There might be. I'm open to ideas, but I don't think it will.
No, I mean, just to evaluate limits that go to
Yeah.
infinity, you have to make them a ratio.
So far, that's the stuff you know how to deal with for the most part.
Okay.
Like the previous example we had was not a ratio, but that was okay. Does that make sense? There's obviously like, you know, you have like a constant, something going to 0, but usually they have to be ratios. Okay, this one, I'll tell you that the answer is 0 if you want to work it out, but you should get 0 for it. Okay. I thought I would bring up one-sided limits again because they're tricky. Do you agree? Okay. So as x goes to 0 minus, where is 1 over x going to go to? It goes to 1 over a negative 0. Do you agree with that? Because x is going to 0, but it's negative, right? What does 1 divided by a small negative 0 make? 1 over x is going to go to positive infinity or negative infinity? Negative infinity. And so what is e to the negative infinity? And it's kind of like bad notation, but if you take e to bigger and bigger negative numbers, this is going to go to 0. Does that make sense? It's kind of using the You can look at what happens to the inside. Inside that exponent, the 1 over x goes to negative infinity as something, as 1 over x goes to negative infinity, e to the stuff is going to go to 0. So this limit is equal to 0. It just occurred to me there's another way to do that. You could think about e to the 1 over x as e to the negative x power. Do you buy that? And if you graph e to the negative x, now why is that not matching up? Oh, I'm so stupid. No, wait, no. My picture doesn't match what it should. That's going to 1. Okay, skip that one for now. Sorry. I don't understand what, either my picture is wrong or something wrong with me. Maybe both. Okay. No picture. First method's good. This one is an example of your squeeze theorem. A big hint that you're going to use the squeeze theorem is that you see a sine or cosine function. That's a huge hint because sine and cosine are stuck between two numbers. That's always how you start your little proofs. You say cosine is in between what two numbers?
Negative 1 and 1.
Negative 1 and 1. And then the thing your next step is to multiply by something so that you have the same expression you have inside your limit. So what would I have to multiply by to make that happen? So multiply this by e to the negative 2x. So negative e to the negative 2x is less than or equal to e to the negative 2x cosine x, which is less than or equal to e to the negative 2x. Okay, now as x goes to infinity, the limit as x goes to infinity of, to take the first one, negative e to the negative 2x is the same thing as the limit x goes to infinity negative 1 over e to the 2x, right? So what is that limit? Negative 1 divided by e to huge power.
0.
0. How about the upper one, the right one? E to the negative 2x. How's that going to be different?
It's 0.
So the question is not, right? It's also going to be 0. But what you really have is you've got one function approaching from the top, one approaching from the bottom, right? And so thus, what is the limit that you care about? What does it have to be?
0.
It has to be 0. By squeeze theorem. And if you were to graph this function, it's going to be one of those functions that has this oscillation, but the oscillations dampen. They get smaller and smaller and smaller. But a big hint, squeeze theorem, is a sine or cosine function. Does that make sense? Because that's how you make this first conclusion, that it's between two numbers. And sine and cosine both have that property. The one I really care about doing is actually the last one. I'll tell you how to start example 10, but I want to go over example 11. So if you're asked to find the horizontal asymptotes, how do you do that? Limit as x goes to where? Nope. Think horizontal is what happens out to the sides. So as x goes to infinity, and the limit as x goes to negative infinity. Okay, so you find that we've been doing limits like that, okay? You're gonna get y equals 2 and y equals -2 in both of those cases. So if you use that function, work it out, you're gonna get +2 for one, -2 for the other. How do you find vertical asymptotes? So it's actually even easier. Technically, that's after simplification, but this one you can't simplify at all. Does that make sense? So in this case, it'd be x equals 4. But the main point is that asking you to find horizontal asymptotes is the same thing as finding the limits at both kinds of infinity. Okay. So last question, I'm going to go maybe a couple minutes, but not too much, is to sketch a rough graph of this by finding its intercepts and the limits as x goes to plus or minus infinity. So x-intercepts you find by setting y 0. So 0 equals x minus 2 to the 4th, x plus 1 cubed, x minus 1. Okay, I'm going to try to draw straight lines. So this should be really, really easy to solve. What numbers make this expression 0?
-1, 1, and 2.
-1, 1, and 2. Does that make sense? Your graph is going to cross the x-axis at -1, 1, and 2. Okay. And the question kind of is like how? Like, does it like totally cross and do this kind of business? Does it like go, you know, like that? It's just kind of, it's hard to say. But it's going to cross in just those spots, okay? Okay, now the next question is to, the next thing I would do is to make a number line. I'm going to plot -1, plot 1, plot 2. And I'm going to test the sign of numbers on either sides. Like not actually how big they're, just like are they positive or negative. It's like if I test something over here, I'll test -2. I'd suggest having a system where you either circle or color code your test numbers so you don't confuse them for the actual zeros. Okay, and then check factor by factor. If you plug -2 into this factor, is the result positive or negative?
Positive.
Positive. Because you take -4 raised to the 4th power, right? In this factor, in the x plus 1, is the result positive or negative? Negative. And in the final factor, is the result positive or negative? Negative. And those numbers are obviously getting like, ignoring their sign, they're getting larger and larger and larger, right? So what is the overall sign of a positive, a negative, and a negative?
Positive.
So it means your function lives up here. And it can't go back down and cross this axis because that would mean it had a 0. Does that make sense? Okay. What's a spectacular test number between -1 and 1? 0. Okay, when you plug in 0, is your first factor positive or negative? Positive. Next factor is?
Positive.
Last factor is?
Negative.
Okay, so overall you're negative there. And the question is, okay, you do go down, and you've got to go back up to cross through that other point. So negative just means below the x-axis. Okay, between 1 and 2, good test point? 1.5, okay. First factor is always positive, isn't it? Because it's raised to the 4th power. Next factor also positive. Next factor also positive. So between 1 and 2, your function will be positive. How far up you go and where that point that is the maximum specifically occurs, you can't figure out because you don't know enough math yet. But the point is it's positive there. It's above the x-axis. And then past 2, what's happening? I think if we tested, say, 3, we would get plus, plus, plus. So also goes back up. So with those questions, I'm not gonna grade if you get your points up or down the right amount. What I'm going to grade is do you have the general shape correct? Does that make sense? Do you cross in the right places, and are you positive or negative where you should be? And you can confirm this by graphing this with a calculator or graphing it on a computer. I mean, you can check your work, but make sure you understand why it does that. Okay? Awesome, good job.